Okay, so can you hear me? Let me see. Save. The mic, okay. I think mic is okay. So we continue this section, 5.3.1, Decomposition of Displacement Gradients. The displacement gradient, partial y uj and partial alpha u beta can be resolved into symmetric and skew-symmetric tensors. Okay, it's okay. I think everything can be symmetric and skew-symmetric. Skew-symmetric means anti-symmetric. It's same as anti-symmetric. So then, strain tensor where E bar ij, E bar alpha beta are symmetric tensor called infinitesimal strain. See, you can see this. This is infinitesimal strains. And R bar ij and R bar alpha beta are skew-symmetric tensor called infinitesimal rotations. So we assume both are infinitesimal. This means small or very small. This can be written as this. Okay, symmetric part is summation. Anti-symmetric part is subtraction. Yeah, subtraction. Ij minus ji, alpha beta minus beta alpha. Then something like that. The Almansi strain component are related. Almansi strain component related to the infinitesimal strain. Infinitesimal strain in the form. This is a little bit confused. So what was the original Almansi? What was the definition? So we use this definition, I think. We take picture. We use this one, right? Oh my god. To turn this off. Turn this function off somehow. Don't know how to do it. So how do you get it? How do you get it from here? Maybe not so difficult. See? I, J, I, J, 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 I. A little bit confused. I think maybe the beta starting point is this one, right? I'd say this one. We also need this one. Oh my god. This one. Then I deleted the old one. Maybe I need my notebook. Okay, let me use this whiteboard. 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 So we have, this is the original definition. Partial IUJ is what? EIJ IJ plus RIJ. So partial alpha big U beta is large E alpha beta plus R alpha beta, something like this. So then what is this? So this part is more like partial I UI UK, correct? This is partial J UK. Then we can see the original definition maybe. Original definition goes like this. IJ, JI, C, E, IJ, 1/2, IJ, I, UJ plus J, UI minus IK, JK. JK. Yeah. So then what do we have? We have, let's see. This thing, this is 1/2 partial I UJ plus partial J UI. So if we put all together, you have this IJJI, IKJK, and here is minus. IJJI, IKJK, and there is a minus. Okay? When everything are small, the Almasi strain is approximately equal to the infinitesimal strain. I think this is typo. Approximately equal to symmetric strain. And this small is more like infinitesimal. If these things are infinitesimal, Almansi strain is approximately equal to the symmetric strain because second order term is neglected. Then further as this, neglecting higher order terms. What do you mean by higher order terms? I don't understand this. Why is this is this like 1 plus something? Large was there any relation? I forgot. Relation between x, this one. I think this is infinitesimal. Okay, this is infinitesimal. Infinitesimal is that means small. So there is a leading term which is 1. Yeah. So neglecting higher order term, 1 is because this is delta function. This is delta function. This is like delta I alpha, for example. And there is a delta function here too. Delta J beta. J beta. There is a summation convention. There is Ij, here I, here J. So you sum over I from 1 to 3, and you sum over J go from 1 to 3. So Ji will be replaced to A alpha and J is replaced to beta. So large EII is small EII. I'm sorry. Large E11 equal small E11. In other words, when the displacement gradients and rotation are small, the material description and spatial description are identical. Okay. Stretch. So now we consider stretch. Let me how many times do I have? See, my thing is very bad. Okay. 15 minutes. Let me continue a little bit. Consider element dx deforming into small dx. Let us attach unit vector large N to dx and small unit vector to dx. Then it's okay, right? In the component form, this is okay. Using ds square is something, d large square is something. I'm a little bit confused about this definition, but should be okay. ds square. How do you get it? I think we just divide this. You can just divide this d large S square. So you just distribute large S here and here. Yeah? So you get this. And each term become unit vector. You can do the same way. Large S you divide by small s square. So you divide by small s, small s. So you get this one. Okay, so the ratio ds divided by d large S is called the stretch. The ratio depends on the orientation of the element. We have lambda n ds over d large S or lambda n small n ds over d large n. For the stretches in the material and spatial description. Interesting, huh? It's a little bit complicated. You have you deform LM. You have this has like three component, right? dx1, dx2, dx3. This one also has three components, dx1, dx2, dx3, right? So then this stretch, you have like a stretch in two directions. So one, you have dx, then there is another small dx. So you need 6 components, right, to define stretch. How come you just have one component? It's interesting. Alpha, beta. So G alpha, beta. G. G contain. I think G. U. U. G. G contain U. Okay. So this G has U. U. For example, U vector. So there is a material coordinate and spatial coordinate, right? Which is also vector. And U, let me change color. U is vector between this, okay? So U contain both component. Yeah? You connect large X and small x. So apparently, it looks as if you have only alpha, beta in this equation, but G implicitly contain the information of U, and U contain the information of small x. So actually this thing, how do you say, stretch contain information of both material coordinate and spatial coordinate. Yeah, so it should be okay. It should be okay. You can write this stretch. This same stretch. I think lambda. I don't know. I hope it's not type. Lambda large n stretch equals small lambda n. Yeah. Yes. For the stretches in the material and spatial description, as special cases, if n equals E1, we get N1 equal 1, N2 equals 3, 2, 0, N3 equals 0. Then lambda 1 is G11 square root. And if small n is E1, you have small n1 equal 1, small n2 equal 2, 0, small n equals 0. I'm sorry, small n3 equals 0. So you have lambda 1 equal 1 over square root G11. Note that lambda 1 not equal small lambda 1 as large n equal E1 does not deform into small n vector equal E1 vector. A similar consideration of unit normals in the other two directions yields the geometrical meaning of the diagonal components of the deformation tensors. Diagonal component of deformation tensor, the meaning is stretch square. Yeah. To see the meaning of the off-diagonal elements we recall that E alpha in the undeformed body maps onto G alpha in the deformed body. If we take two orthogonal unit vectors E1 and E2, their images are G1 and G2. If theta 1, 2 denotes the angle between G1 and G2, we have cosine theta 1, 2 is G1 dot G2 divided by absolute value of G1 times G2. I think I get this. G1 indicates the distortion of original angle of how do you get this? G1 was this definition of G? There was some definition of G. I think this is not what we need is G this one. This is what we want. G. I think we promoted G from vector to tensor at some point. So here G is still vector, but then at some point I think we promote it to tensor. Maybe it's this point. Yeah, this one. G alpha beta is our old metric tensor, which is the dot product of the base vectors. So this is exactly the definition. So I would say this is the definition. This is definition. This is definition. Then how? Okay. So this one, this is like this. G no is like G1 dotted with G1 absolute value. So this is vector, right? So then, because this is the tensor component, So this is like square root. So this is tensor component. So G11. So here, this is also same. G2 vector no is G2 vector dotted with G2 vector 1 over 1 half. So then this is G11 1 half. So you obtain this one. Thus, G12 indicates the distortion of the original angle of 90 degree. Why? I don't know. I don't see much sense here. Okay. This is just like this. If you have E1, you have E2 in material coordinate, right? Then this goes like G1, which is vector, and G2, which is also vector, right? So originally in material coordinate, this was right angle, 90 degree. But then after deformation, the angle change to this angle. That's it. I think that's it. I think the important picture we should remember is this one. Some distortion. So this one we should remember. So originally there was the angle between E1 and E2 is 90 degree, but then this becomes like this degree. So and what is this degree? We call cosine theta 1, 2. We call this angle theta 1, 2, and this angle is given by G1 dotted with G2, which is both vector, divided by square root G11 G22. That's it. Let's see. Displacement finished. Stretch finished. Extension. May I take a break maybe? Let me see. What time? I don't see the time. I think okay, we did 35 minutes. So let me take break. Okay, so I will come back. See you.